Okay, so hopefully you've looked at the video with the Excel spreadsheet, looking at the uniform distribution and what happens when we take sample means of several samples, 20 samples, and look at the distribution of those sample means and the mean and the standard deviation. We're going to summarize now with the central limit theorem, kind of what's going on there with the sample mean. So if we let x be a random variable with any distribution, so we looked at uniform, it could be any other distribution that we know what that distribution is or we don't know what it is. But we do assume that it does have some mean value and a standard deviation. So if we take for a sample size n, the sampling distribution of x bar, okay, that is the probability distribution of x bar, the sample mean, will be approximately normal. All right, so maybe you kind of could tell that's where we were going just based on how those histograms were looking. None of them looked exactly normal, but they were looking kind of peaky in the middle and then tails on either side. X bar, so that's the sampling distribution of X bar. It's approximately normal, right? If we want to think about what the mean of X bar is, and we can denote that with a mu with a little subscript of X bar, well, that's actually going to be equal to the mean of the distribution of X, whatever our original random variable is. And the standard deviation of the sample mean of X bar, all right, it's not equal to the standard deviation of X, it's equal to the standard deviation of X divided by the square root of the sample size. All right, this is also called the standard error of the mean. All right, now if the standard deviation is greater than 1, this value is going to be less than the standard deviation, all right, because we're dividing it by something which is going to make it smaller. Now this value is also called the standard error of the mean. So another thing we can call the standard deviation of X bar is the standard error of the mean. Okay, now we can summarize all of this by putting this in our random variable distribution notation. So we have the X bar is approximately distributed as normal, and it's got a mean of mu, all right, from the original distribution, and standard deviation of the original sigma, the original standard deviation divided by the square root of n. All right, so if we want to improve the approximation, all right, if we want to make it a better approximation, well, we're going to want to increase the sample size. So the larger the sample size, the better the normal approximation. Okay, so now let's take our Excel example. We had a random variable x, and we said that it was uniform and it had a minimum value of 23, maximum value of 43. The mean is 33, and we calculated the standard deviation. And just a refresher there, it's the difference between the min and the max divided by the square root of 12, which if we round to one decimal place, we get 5.8. So if we sketch the density curve, okay, so along the horizontal, we have the x values, and those go from 23 to 43, and the height is 1 over the difference between the min and the max, so that was 20. All right, because that's our uniform distribution. Okay, now we can find the probability that x is between 30 and 33. So if we draw that on the density curve, all right, if that's 30, that's 33. We're looking for this shaded area. So to find that probability, we know that we take that f of x at 1 over 20 times the difference between 33 and 30. So we get 3 over 20, or 0.15. Okay, so that was finding a probability for the original random variable x. All right, so an individual value from that distribution. So the probability that x is between 30 and 33 is 0.15, or 15%. Now let's look at the sample mean. So based on the central limit theorem, we want to complete the following, assuming that we have a sample of size 10. Okay, so x bar then is normal, all right, based on the central limit theorem, and its mean is, it's going to be the same as our uniform random variable, it's 33, and the standard deviation, all right, will be that 5.8 divided by the square root of 10. Okay, which is approximately 1.8. Okay, if we sketch the density curve for x bar, all right, well, we said it was normal, so, okay, we're going to have that normal curve. And instead of having x along the horizontal, we've got x bar. And it's centered at that mean of 33. Okay, so we can say that our standard deviation here is 1.8. Okay, now let's find the probability about x bar. So because x bar is normal, we are not going to use the uniform distribution to find this probability. We're going to use the normal distribution. So we want to find z-scores and find this probability based on those z-scores. So the z-score for 30, you take 30 minus 33, divide that by, now to be completely accurate to get the z-scores, we don't want to use the standard deviation that we rounded. So we'll use the 5.8 over the square root of 10 and plug that into the calculator, and then round that to 2 decimal places, and that's going to be a negative 1.64. Okay, z-score for 33, hopefully you can see that that's just going to be 0. Right, you got 33 minus 33 in the numerator, so we get 0. So our probability then is the probability that z is between negative 1.64 and 0. So using a normal distribution tool online, well, the probability to the left of 0, or the left of 33, is 0.5, all right, that's half the distribution, so it's 0.5. And the area to the left of negative 1.64 is 0.0505. So doing that subtraction, we get 0.4495. Okay, now remember that when we found the probability that x was between 30 and 33, we got something much lower. We got 0.15, and here we get a probability of 0.4495. Okay, now let's look at a different sample size. Suppose we have a sample size of 25. Let's see how things change here. Well, we still have x bar as normal, and it's a larger sample size, so it's going to be a better approximation. All right, the mean is 33, and the standard deviation, take the 5.8, divide by square root of 25. So that's going to give us a different standard deviation. It's approximately 1.2 when n is equal to 25. So the sample size changes the standard deviation. So that standard deviation of x bar depends on sample size. So now let's sketch the density curve for x bar when n is 25 on the curve that we have above. Okay, so really all we have to go by is it's going to have the same mean. It has a smaller standard deviation. So what does that say about the curve? All right, well, it means that it's going to be less spread out and it's going to be taller and it's still going to be centered at 33. Okay, so this green one is standard deviation of x bar approximately 1.2, and that's with n is equal to 25, and I'll label this 1.8 is when n is equal to 10. All right, now let's find the probability of x bar when n is 25. So again, we got to find z-scores. So z equal to 30 minus 33 over 5.8 divided by square root of 25. Okay, that's going to give us a z-score of negative 2.59. So this is a probability that z is between negative 2.59 and it's 33 is still going to be 0 for the z-score. Okay, so we start off with that 0.5. All right, that's the area to the left of 0. And then subtract off the area to the left of negative 2.59, and we're subtracting off 0.0048. And that's a probability of 0.4952. So if we make some observations about the standard deviation, if we started off with x having a standard deviation of 5.8, and then when we had a sample size of 10, okay, the standard deviation of the sample mean was 1.8. And then when we had sample size of 25, the standard deviation of x bar was even smaller at 1.2. Okay, so what we can say is that the standard deviation of x bar is less than the standard deviation of the random variable, and as the larger the n, we get a smaller standard deviation for x bar. Okay, second observation, we compare probabilities. So the probability, if we just looked at x, if it was the probability that x is between 30 and 33, we had probability of 0.15. And when n is equal to 10, the probability that x bar is between 30 and 33 is equal to 0.4495. And when we increase that sample size to 25, the probability that x bar is between 30 and 33 is even larger, 0.4452, or I'm sorry, 0.4952. Okay, so the probability is getting larger as we go from the random variable, a probability about an individual value, and compared to the probability about sample mean. And then the probability increases as the sample size increases. Okay, so let's look at this next example, and we actually have a nice picture of density curves for a random variable x. Okay, that is this population distribution right down here. So this is X, this one that's, you know, pretty flat. And we're told that it has a standard deviation of 16. Okay. Now, we also have a distribution of X bar when n is 4 that's also listed there. So it is still centered at 50. Okay, but the standard deviation is 16 divided by the square root of 4. So 16 divided by 2, standard deviation is less, it's 8. All right, and we can tell it's less spread out than the original distribution. And then when we have n equals 10, standard deviation of the sample mean is 16 divided by the square root of 10. All right, if we round to 1 decimal place, we get approximately 5.1. Okay, so even smaller. And you can tell by the picture it's less spread out, okay? The peak is taller. Now, if we compare probabilities, if we start with the probability that x, the original random variable x, an individual value is in between 47 and 52, if we find that probability. All right, first we got to find z-scores. For z equal to 47, 47 minus 50 over 16, we get a z-score of negative 0.19. And for 52, subtract 50, divide by 16. That gives us a z-score of 0.125. So we're looking for the probability that z is between negative 0.19 and a positive 0.125. So from our online tool, we're going to get 0.5497 minus 0.4247. So probability of 0.125. Okay, so if we shade the area on our density curve, all right, let's say our 47 is right there and our 52 is right there. Okay, so this is going up to our curve for x, all right, the population, and I'll shade that in, I'll just do that one in red. Okay, it's this area right here, and that area is 0.125. Okay, now let's look at sample mean with sample size of 4. So now we got to find different z-scores, right? We have different standard deviation, so it's going to change the z-scores. So take 47 minus 50, all right, divide that by 16 over the square root of 4. So we get a z-value of negative 0.375, and then for 52, we get z-score of a positive 0.25. So this probability then is the probability that z is between negative 0.375 and a positive 0.25. All right, so using our online tool, we're going to get a 0.5987 minus 0.3538. So probability of 0.2449. Okay, so now let's shade this on that density curve. So we're still going from 47 to 52, but now we're looking at that density curve for x bar when n is 4. So that is going to add some area, right? We kind of extend that up there. That's going to add this area right here. All right, still between 47 and 52, but because that density curve is higher, we're adding that area. Okay, so yeah, we went from 0.125 to 0.2449. Curve, shade that area. All right, still between 47 and 52. Okay, but now we go up to this density curve for n equals to 10. And we have a smaller standard deviation. So the peak is higher and there is more area, so a larger probability. Okay, now let's look at sample mean x bar when n is 10. All right, same probability values, 47 and 52. Let's find z-scores. So take 47 minus 50 over, now we got standard deviation of 16 divided by the square root of 10. So we get z-score of negative 0.59. And then 52 minus 50 over 16 divided by the square root of 10. We get z-score of 0.4. Okay, find that probability then is the probability that z is between negative 0.59 and 0.4. So we take from our online tool, we get 0.6554 minus 0.2776. So probability is 0.3778. Okay, so like you would expect, it's higher. If we go back and put. Okay, here we have another example. X is a random variable that stands for a mid-semester grade, and it comes from a distribution that all we know about it is that it is skewed to the left. It's left skewed, and it has a mean 79 and a standard deviation of 12. And let's suppose we have a sample of 20 students of their mid-semester grades. So let's first off sketch a distribution of X. Okay, so all we know that it is skewed left. So remember that means that the tail is on the left. So maybe it looks something like that. That's really all we know about it. And we know that the mean is 79 and the standard deviation is 12. Can we find a probability that X is between 70 and 80? Well, since we don't know what distribution this is, and all we know that it is left distributed, we cannot, okay? We do not have a formula, we don't have a table. We just are sort of sketching a very rough sketch of the distribution. So we can't find that probability for X. But what about X bar? Do we know that distribution? Well, X bar is based on the central limit theorem, approximately normal with mean equal to the original distribution mean and standard deviation equal to the original standard deviation divided by the square root of the sample size, all right, which in this case is 20. Okay, so that is approximately 2.7. All right, sketch a density curve for X bar. Okay, it is normal. Okay, so we know that it's going to have that normal shape with a mean of 79. Now, because X bar is normal and we have access to probability tables for for normal, we can find the probability for X bar, the sample mean. All right, even though we weren't able to find the probability for X, an individual mid-semester grade. Okay, we can't find the probability that an individual mid-semester grade is between 75 and 80, but we can find the probability that a sample mean of 20 mid-semester grades is between 75 and 80. Okay, so we just need to find the z-scores. So for 75, we get a z-score of negative 1.49, and for 80, we get z-score of 0.37. So finding probability that z is between negative 1.49 and 0.37. Using our online tool, we got 0.6443 minus 0.0681. So yeah, 0.5762. Okay. Last question is, would this probability be higher or lower if n is equal to 27? All right, so if n is equal to 27, then the standard deviation would be smaller. And the effect on that probability, the probability would be higher or larger. All right, with a larger n, a larger sample size.